So I think we have to move to the next talk, which was already advocated in the previous one. And this will be by Martin Steil from Darmstadt. And he will talk about inhomogeneous chiral condensates within the Functional Renormalization Group.
Yes, thank you, Michael. Can you hear me all right?
Yes.
Okay, then I start sharing my screen. Okay. Can you see this, the slides?
Yeah.
Okay, then I will start. So as already advertised, I will talk about inhomogeneous chiral condensates within the Functional Renormalization Group. And this is work done in collaboration with my PhD supervisor and the chair of this session, Michael Bubala, and with Bernd Jochen Schäfer. And this work is also part of a sub-project of the CRC Transregio 211. So a lot of people are in somewhere or another involved, and not necessarily all are listed now here as co-authors or collaborators. And before I continue, let me thank the organizers for the great opportunity to present our work here. So with this, I come to my outline. So I will start with a very brief motivational introduction. I will keep this even briefer than usual because Stefano already did such a great job setting me up here. Then I will talk about inhomogeneous chiral condensates within the FRG framework. Before I do this, I will very briefly introduce the FRG. And then I will come to two main parts of this talk, two main chapters if you want. And they are both related to FRG-based mean field calculations. And the first one I have titled here the naive way, and the second one the consistent way. A more fitting title would be the wrong way and the better way, but I will come to all of this. And I will conclude basically the second part with phase diagrams. So kind of the best solution we have so far. And then I will finish with a summary and an outlook. Okay, Stefano already discussed this, but let me just briefly review it or point one plot out, which Stefano already had on his slides. And this is one long-standing result for the two-flavor quark-meson model in mean field. So this is a result almost 30 years old by Broniewski et al. And they basically found in those chiral low energy effective models, if you drop the usually tacit assumption that the chiral condensate is constant in space, then you in fact find inhomogeneous chiral condensates. And maybe I just flip the axis here for consistency reasons. So we find actually such a inhomogeneous window in these models in mean field at low temperatures and intermediate, or if you want, high chemical potentials, usually around the first order phase transition, or here actually overlapping the first order phase transition, which you had if you would just consider homogeneous condensation. And this is basically a long-standing mean field result in those low energy effective models. But one major open question is whether this picture and actually this inhomogeneous window is stable against bosonic quantum fluctuations, because in mean field you usually consider fermionic fluctuations. And the question is what happens if you consider bosonic quantum and thermal fluctuations. And there's actually some work done in this direction, recent work. I will just present two results here. Those are both results based on FRG stability analysis. Those stability analyses are very similar to the ones Stefano already discussed and introduced in mean field. So what one usually does is one computes the two-point function for the mesons and looks for instabilities. And here on the left, we have a work of Ralf Arno Triepold and collaborators. This is a work done in the two-flavor quark-meson with the FRG. And here we, in fact, find a region where one might expect such an instability, which could be a hint for such an inhomogeneous phase here beyond mean field. And on the right here, we have a state-of-the-art, highly involved 2+1 flavor QCD computation also performed with the FRG. And this study was limited to higher temperatures, but here we also see and find such instabilities of the 2-point functions, which could be a hint for inhomogeneous condensation, even in such a context where we are actually not considering just the low energy effective model of QCD, but really do the full QCD computation. But there are still a lot of open questions, especially at low temperatures, and also those were just results based on stability analysis and not necessarily on an explicit inhomogeneous computation. So this is basically the main motivation for our work is this open question regarding the stability of inhomogeneous chiral condensates against quantum and thermal fluctuations. What I will talk about in the next few minutes is really our current goal, and this is a study of the effects of bosonic and fermionic quantum fluctuations in the two-flavor quark-meson model in the chiral limit. So this is one of the simplest low-energy effective models of QCD we have, and I will also consider a specific ansatz for the inhomogeneous chiral condensates, the so-called chiral density wave, which Stefano already introduced. And I will come to this why I choose this ansatz and why different ansatz would be disadvantageous. The methods I will use, or the method I use, is the Functional Renormalization Group, because the Functional Renormalization Group is a highly potent tool to study the effects of quantum fluctuations, because at its core, the Functional Renormalization Group is tasked with integrating out quantum fluctuations from a classical action. And a nice thing is that this analytical method allows for computations at finite non-zero chemical potential and temperature. And in principle, one can include explicit inhomogeneous chiral condensates, but it's practically extremely challenging. But formally, it's not necessarily problematic. So maybe just one very short slide about the Functional Renormalization Group. So the Functional Renormalization Group is a functional implementation of Wilson's RG approach. So basically the idea is to construct this object gamma k, which is the so-called scale-dependent effective action. And this scale-dependent effective action interpolates between a classical action in the ultraviolet at a scale lambda and the full quantum effective action, the generating functional of 1pi correlation functions in the infrared. And the FRG now tells us how to evolve this effective action from the UV to the IR. And this evolution is basically encoded in the famous Wetterich equation, which is written down here. And this is a functional integral differential equation, which really describes this scale evolution exactly. So this equation is exact. It's basically a differential formulation of the path integral formulation. And diagrammatically, it has a rather simple form. So it's just this one loop diagram with the regulator insertion here. But the important point is that in this propagator here, we really have the full propagator of the theory, the regulated propagator of the theory. So this is really a non-perturbative equation. And in fact, the nature of this equation as a functional differential equation makes it almost impossible for all realistic models of interest to solve this exact equation exactly. So one usually needs to deploy some truncation scheme and has to ensure that this truncation scheme is sorted out well and that the truncation is controlled, but this is a very difficult task in general. So with this, let me show you the model I will use. I will use the two-flavor quark-meson model. Stefano already introduced this model. And in this FRG context, I will consider this quark-meson model in a so-called local potential approximation, which basically amounts to making an ansatz for the effective average action by basically expanding all possible terms in derivatives and only keeping the lowest order, the zeroth order in derivatives. So the only scale-dependent property or quantity I will discuss and consider for the moment is a scale-dependent effective potential. So this is basically a mesonic interaction potential, which includes the dynamic of the system. And if one now takes this ansatz and plugs it into the Wetterich equation, one also has to evaluate both sides of the equation on some background configuration. And usually one chooses a homogeneous background configuration. But since I will want to study inhomogeneous chiral condensates, I will consider an inhomogeneous one. And explicitly, I choose the chiral density wave. So this amounts to making an ansatz for the classical mesonical fields, which is just a simple plane wave. So we have a cosine in the sigma direction and a sine in the pi3 direction with some amplitude q. And this ansatz has some very, very special properties. For example, the O4 invariant, so just the square of this expression, actually does not depend on position, which is extremely nice, especially considering that this here appears in the argument of the interaction potential. And another very important identity is Euler's formula here, which is if I just consider this combination of sigma and pi3, I can rewrite this again as a simple plane wave. And this is one of the analytic properties which has to be used extensively in these analytical studies with the chiral density wave. So now you could ask yourself, why this ansatz? Why do we have to make such a specific ansatz? Why do we need those analytic properties? And the main challenge here is the challenge Stefano already mentioned, and actually a challenge which is not specific to the FRG. The problem is if you consider inhomogeneous chiral condensates, your two-point functions become explicitly position dependent. So we have here the full two-point function of the fermions and the two-point function of the bosons. And because we allow for an inhomogeneous condensate, we have here explicit position dependence. And if we now transform those expressions into a momentum space, those explicit position dependencies manifest as non-diagonal couplings in momentum space. And in fact, we have to invert those two-point functions in order to compute our propagators for the Wetterich equation, or basically if we talk in terms of mean field, in order to compute our loop integrals. And such an inversion of non-diagonal infinite dimensional matrices is very, very challenging. So we take the simple solution. We just consider a very specific ansatz and massage those expressions, because it turns out if you consider the chiral density wave, you can find unitary transformations to diagonalize those two-point functions in momentum space. Or talking in position space, using unitary transformations, you can eliminate those explicit position dependencies here. And actually for the fermionic sector, such a transformation has been known for a long time. So in the context of pion condensation, this goes back to Daughtry and Niemann, but in the context of superconductivity for Fulle-Ferrel solutions or Fulle-Ferrel Ansätze, this probably goes back even further, but here we can basically reintroduce this old idea into the FRG formalism and basically use this unitary transformation UF to diagonalize gamma 0 times the two-point functions of the fermions. And actually, what we were able to do, and as far as I know, we are the first ones to do so, is to construct a unitary transformation for the bosonic sector, which is basically based on this identity. and looking at the expressions long enough. But it turns out using these unitary transformations for the mesonic two-point function, we can also diagonalize the mesonic two-point functions. And this basically amounts, both of those transformations basically amount to a change of coordinates in this classical field space. Yes, and now if we use those unitary transformations and diagonalize our two-point functions, we then can basically use standard techniques also shared with the homogeneous computation to really compute our flow equation. And the result is the LPA flow equation for the effective potential with chiral density wave condensates. This takes a very generic form, and in fact it's almost the same form as in the homogeneous case. The only difference here is now that we have here the eigenvalues of the chiral density wave and not the homogeneous eigenvalues. And the only thing we had to do to basically come to this conclusion is to choose an explicit FRG regulator. So this is basically this object which was introduced here, which mitigates this scale evolution. And this is basically a free parameter in the FRG. It's just these regulator functions only have to fulfill certain properties. And at this point, we made an explicit choice. We choose a three-dimensional regulator to facilitate computations at finite temperature. So basically, in order to perform the Matsubara frequency summations. And now this eigenvalue spectrum is a bit more complicated than in the homogeneous case. So for the fermions, we have this rather complicated expression, which involves the amplitude of the chiral density wave and those shifted regulated momenta, pk super q, where q again is the wave vector of the chiral density wave. And those are very similar to the ones which one also encounters in conventional mean field studies. And now the bosonic eigenvalues are basically the new thing here. So we recover two eigenvalues which are identical to the situation in the homogeneous phase. Those are the eigenvalues related to the pi1 and pi2 direction. And then we have two new eigenvalues which are now really related to this chiral density wave. And if we take the homogeneous limit, so if we set q equal to 0, we recover the homogeneous eigenvalues. So this is a nice consistency check, because one very nice thing about the chiral density wave is if we set this modulation momentum to 0, we recover the homogeneous result. Okay, so now we in principle have this flow equation, and this is now just a partial differential equation for this scale-dependent potential. But the practical solution is actually rather complicated, because this is a very complicated differential equation. So in the first step, we have tackled this problem in parts. And for the following, we will just consider basically the fermionic contribution related to those fermionic eigenvalues. So basically, we ignore for the moment the bosonic fluctuations here. Diagrammatically, this then boils down to just considering the fermionic loop. And then this partial differential equation for the effective potential becomes an integral equation, and we can just integrate it up. And if we then choose a UV initial condition and an explicit regulator, we can basically compute phase diagrams after we fit our model parameters to observables. And in the first step, in the what I called in the beginning the naive mean field computations, we have fitted those parameters to the Bayer pine decay constant, the sigma curvature mass, and the quark mass. And let me now come, after this rather formula heavy part, to some pictures. So if we fit the following parameters up here, we basically arrive at such a phase diagram in the homogeneous case. So currently we just consider homogeneous condensation, and lambda here is are now different values of the UV initial scale. and we basically recover the well-known picture here for homogeneous mean field phase diagram of the quark-meson model. But if we now consider inhomogeneous condensation, so if we zoom in into this window here, we find the following. We have here now on the left, again, this phase diagram in the T mu plane, and color-coded here in this color scheme on the left, we have the amplitude of the chiral density wave, and on the right, we have the wave vector. And what we find now, if we allow for inhomogeneous condensation, is that we don't see an inhomogeneous window. So this is rather surprising because earlier mean field studies have shown such an inhomogeneous window. Now the question was, what happened with the inhomogeneous window? And to investigate this, I first further decreased the UV initial scale. And if you decrease the UV initial scale further, the inhomogeneous window reappears. But the problem is, with such a low UV initial scale, this UV initial scale is actually lower than the external and internal characteristic scales of our model. We really find inconsistencies here, and the phase diagram is also not stable against variations in this UV initial scale, which basically violates RG consistency. So this is really unpleasant, and this is not what we would have expected from existing mean field studies, because we have existing mean field studies, which Stefano already mentioned. Here I have shown two results for the quark-meson model in the chiral limit of existing mean field studies in the renormalized limit. And here we really find this well-known picture that we have this small inhomogeneous window at low temperatures and high densities, but this is really in the renormalized limit, and this is a stable result. And in this renormalized limit, we would also expect those results to be scheme independent, which they are between those two computations. So the question is, what is wrong with our FRG-based mean field computations? And it turns out that this rather naive or hands-on approach to this RG-based mean field calculations is the wrong one. And one has to do a bit more work. And this is basically related to two facts. The first problem is that our naive parameter fitting procedure is just insufficient and actually inconsistent, because in fact, if we want to study inhomogeneous phases, we really have to fit pole masses and a renormalized P on decay constant, and not the bare quantities. The reason for this is that the inhomogeneous phase is basically related to an instability in the mesonic two-point function, and you really have to treat this two-point function consistently, and also include the effects and the fluctuations on the level of these two-point functions in your parameter fitting procedure. And this idea is basically motivated now in this context by pre-existing mean field studies, where this was also necessary to get meaningful results. And the next part is really related to RG consistency. And this basically means that our phase diagram or our infrared action should be independent of our UV initial scale for all external parameters. So here now temperature and chemical potential. And basically to fix this problem, we follow Jens Braun, Mark Leonard, and Jan Pawlowski, and we implement an RG consistent mean field approach, which basically, the idea, I will just talk about this briefly. If we have time, I have backup slides for this. But the idea is now to fix.
Try to finish within the next 4 or 5 minutes.
Okay. Yeah, and the idea here is now really to fix the action at a lower scale and reconstruct UV completion. And doing this, following those authors here, we can really enforce RG consistencies for arbitrary initial scales lambda prime. And this, on the mean field level, this is actually rather easy to implement. So let me just now show you results regarding this RG consistent mean field approach. If we now consider this and again look at the phase diagram with our naive parameter fitting, and now just use an RG consistent reconstruction and increase our UV initial scale, we actually recover phase diagrams which look plausible. But we are again left with the problem, even when we consider this RG consistent mean field studies, that we cannot increase our initial scale lambda prime to arbitrary values because the inhomogeneous window just vanishes. But at least with this RG consistent reconstruction, we can get meaningful phase diagrams and consistent phase diagrams even with this naive parameter fitting. And basically, if we increase our UV initial scale using the RG consistent reconstruction to a reasonable value, we get stable results. And in this RG consistent setup, we can also recover the standard mean field. I will just skip this for time reasons. Basically now I come to the the improved parameter fitting, and this is basically based on the mesonic two-point functions which we can compute in the FRG. Let me maybe just skip the formulas and come to some results. Maybe just one important aspect here is if we do this parameter fitting with our three-dimensional regulators, we have to take care of Poincare invariance because we have explicitly broken it. And I have come up with two schemes here. I have no time to go into details. I will just show you plots. And maybe let me just come to this plot, or maybe just the phase diagrams. So if we really use this RG consistent mean field setting with our improved parameter fitting scheme, now we can really get meaningful phase diagrams which are also stable against increase in the UV initial scale lambda prime. And it doesn't really matter if we use this RP prime scheme, which I skipped, or if we do another scheme here, we get meaningful results here. The only issue now is because we have this the breaking of Poincare invariance because of our chosen regulators, we are very sensitive to the sigma meson mass, and we also do not recover this nice feature that if we choose the sigma meson mass as 2 times the quark mass, that the Lifshitz point and the critical point coincide. So this is kind of lost here. And to really fix this, one would have to use a covariant regulator, which is a bit involved in computations at finite temperature. Yes, and maybe with this, let me just come to the conclusion and summarize our results. So if we do our mean field studies in the FRG context carefully, meaning that we really fit our parameters carefully and also take vacuum fluctuations on the mesonic two-point functions into account, and if we ensure RG consistency, we can get meaningful phase diagrams and results which are in qualitative agreement with existing results. But we still have small deviations because we have chosen spatial regulators, and those regulators break Poincare invariance in vacuum. To really fix this would need further work, which I have hinted here in the outlook. One would really have to use 4-dimensional regulators. What we are currently working on is a full numerical solution of the flow equations, because I showed you the flow equations including bosonic fluctuations, but I have only shown you mean field results so far. But this is really ongoing, and also in this A0C sub-project of our CRC, this is currently in the work. And two further points in the outlook. What one should also do is really compare these explicit results for the chiral density wave with results from a stability analysis. This has not been done so far, but is also on the agenda. And then a very big part for the future, and maybe also future generations of PhD students or researchers, is really do these kinds of studies with an improved truncation beyond LPA. because this very simple truncation in the FRG setting is just not really sufficient to give a definitive answer to our question whether the inhomogeneous window is stable against thermal or quantum fluctuations. Because to really answer this and get an answer which is physical in a sense or has predictive power, we need to improve our truncation. Yes, and with this, I want to thank you for your attention, and maybe we have time for some discussion, or we discussed in the discussion section.
Yeah, thank you, Martin. There is a question again by Nuksha Mahaldiani.
Thank you. Indeed, I have two short questions. First of all, in the exact renormalization group equation, you made simplification. You neglect the duct diagram.
I neglect what, excuse me?
You had the two terms, you just, in the exact equation, after you had two terms, and one of them you neglected later.
Yeah, exactly. You mean here, yeah, for this.
Yes.
Values, yes.
You may do it if it is small. If it is not small, you cannot do it.
Yeah, no.
Obtain running.
Yeah, you are right.
If it is small, you may try to use perturbation theory.
No, I mean, the idea, the goal in the end would really to don't neglect this, those contributions, because this actually these fluctuations and this contribution is maybe the main reason of these studies, to really include them, and we actually have an equation for them. But in the first step, we just did not have the right feeling and the right numerics to tackle this. But one should really include this. I mean, there is no reason to expect that those are small, and one can treat them non-perturbatively in the FRG. This was just now for the talk, really an effort to first recover known results and then really study those unknown new results stemming from those bosonic fluctuations. Those can definitely not be neglected with any physical arguments, at least in this model.
Anyway, you may try to neglect in zeroth approximation, and in the first approximation in perturbation theory, try to find contribution. It's easier than to solve.
Yeah. Maybe one could look at some.
Second question is that in the original model, you had usual coupling constant, G small. So you may try also find evolution of that fine structure constant. And if you have some results for that coupling constant.
Yeah, this is actually an improvement of the truncation.
Interesting to have.
So if one would go beyond this so-called local potential approximation, one would allow for further scale-dependent couplings, and the first one would allow in a derivative expansion. And actually, to be precise, one should actually in the lowest order derivative expansion also consider this coupling constant to be running and field dependent. So this would be a first step for further improvement to allow for more running couplings in this ansatz, and also for wave function renormalizations and so on.
It's curious to know infrared limit of that fine structure constant for G squared divided by 4 pi. What is it in the infrared limit?
So I mean, this is the Yukawa coupling in this model, and for computations there are results.
Because you have phenomenological estimations of that constant, and there it's very difficult to extract from the.
Yeah, I mean, this is something I haven't necessarily mentioned, but I mean, this model is very too simple to really consider real phenomenology and real physics, because I mean, this is a two-flavor model in the chiral limit, and to really describe nature with this is a bit of a stretch. So this is why I kept the results of the discussion on a rather theoretical level, without necessarily focusing too much on the right physical parameters to fit But if one would have a more involved model, one could definitely also try to make informed decisions about those couplings from phenomenology and from experiment.
So I think we should shift this kind of discussion to the discussion session later. I see one more question by Andreas Wipf, who is anyway the next speaker.
Yeah, I have to log in anyhow.
A short question directly to this talk, otherwise.
Yeah, just a very short question.
Yes, okay.
Yeah.
I think you put this RG consistency condition, which was important. I guess this is the result that the theory is non-renormalizable, and you really, in principle, should use the UV completion, which is something like QCD. So my question really is, how did you implement this without knowing the UV completions?
Okay, I mean, this is a very good point, and maybe this statement here is a bit dangerous without elaborating. So the quark-meson model is renormalizable, and also in this mean field setting. And what this basically means here is really to use the model itself to construct UV completion. So really to engineer this initial condition within the model. So this is not a physical UV completion you can't really get QCD out of the quark-meson model, but this is just basically integrating up the Wetterich equation to really enforce this condition here at finite and non-vanishing temperatures and chemical potential. Maybe we have time in the discussion sessions to elaborate on this a bit further. I also have some sketches in the appendix where this is laid out, but this is just a technical point within the model to achieve RG consistency and not necessarily a UV completion by means of a more involved model or, for example, QCD.
Okay, I see.
Okay, then thank you again, Martin.
Yeah.
Unfortunately, we are already 10 minutes behind schedule, but it's always nice to have interesting discussions.